a given data set as a function of the number of samples. So probably there's not much point in explaining what a learning curve is. All of us somehow know. Still, we're going to dig a bit deeper because there's probably something that anybody can even take away only on the definition of learning curves. But here, as I already said, a lot will be on the question of how can we use these learning curves as valuable resources for decision-making, specifically automated decision-making. So it's not only to use the learning curves as a resource for the data scientists, but also as a formal resource that algorithms can use to make decisions. I will talk about 3 different decision type situations, or types of decision situations, but already as a teaser. So obviously they are very useful for data acquisition. So you can use them to decide you want more data points or acquire more data points or any algorithm for more time. But even more importantly, maybe nowadays is the point of model selection, because thanks to automated machine learning, the question of model induction and model selection has seen a new uprise. And we will talk a lot about how can we use learning curves to improve decision-making during the model selection process, which, as we all know, is oftentimes quite costly. So this talk is mainly based on a survey paper that we have recently published. So Jan and me have published this this year at Archive. It's still under review for a journal, and hopefully we'll see that soon. So if you want to read more details on this, you can watch out for the Archive version. And the talk is split into 3 parts. So first we'll talk a bit about the background on learning curves. Then I will give really a quick overlook about how can we then use learning curves for decision making. And in the third part, Jan will give an overview of the literature, which is surprisingly rather small. So learning curves have been around almost since the beginning of machine learning in the maybe not in the beginning, but they have been around since the 80s, 90s, early 90s. And it's really surprising how little research has been conducted on learning curves, even though they are so useful and so known to everybody. Yeah? But probably this will change in the upcoming years. So as a background on learning curves, let's start with the simplest case, because we will see a couple of performance curves now. And let's start with the one that is probably most known to us, which is, well, we have some learner, which is, so we're focusing first on this green curve here, which says standard curve. And there's not a lot of formalism in this talk, but since we can easily mix up different concepts of different types of learning curves, at least there's some notion. Okay, so what we have here to describe these learning curves is a function C just for curve, which has 2 arguments, A, which is the learning algorithm, and S is, in this case here, the sample size. So what does A do? A takes some set of training data of some size, which is here S, and infers a model from that, what we are typically calling model or hypothesis. And this hypothesis has some performance, which we typically ideally measure with the out-of-sample performance, which we all know is not possible. But here you define some loss function like the or some performance measure like the accuracy, the error rate, the F measure, or whatsoever. We say, okay, how well does this model, this algorithm A induce, given some training set, perform on every possible data that can come into this model for being inquired for a prediction, okay? So here we're taking the expected value across all data sets that can be used for training with this learner. So this is what this part of the formalism here is saying. So among committing to a specific source of data, for example, I don't know, some image generation process for cars, for example, or for different types of images. So across all the possible data sets that contain exactly 1,000 images, for example, we average what's the generalization performance of the models that are being trained with a particular learner A on those data sets. And this is what gives us this green curve here. This is a function for a concrete learner A that could be a concrete neural network with a concrete hyperparameter configuration. This is the result of, okay, so for a neural network, it would be the result of convergence. Let's take a different example. Let's take maybe a decision tree or a random forest. So you train this model, you obtain, or you get a model with this learner, and then this model will have some generalization performance, and that is what we see here as a function of the numbers of instances used during training, right? So that's a lot of words for something that everybody knows already, but yeah, we already see here in this figure that there is even different types of learning curves for this specific situation where we have it as a function of the samples, because there are other types of learning procedures, like, for example, the incremental learners, like neural networks or other, which are maybe restricted to only receiving one instance at a time. And then they must, within short time, incorporate and update their model based on this new instance. So in this case, showing the same amount of information to the learner can imply that it learns slower, because it doesn't memorize really all the instances. It just updates the model once at a time. And that makes, if you show it 100 samples, but not in a batch mode, but one at a time, implies that it needs more time to learn the concept well. Yeah? So this is why one could say, okay, in stream, so if you don't learn from in batch mode, but from streams, you're a bit more delayed in this process. On the other side, you could say, okay, in fact, where do these samples here come from? Maybe these are the results of some active learning process. So we have some data at some point of time, then we ask, okay, which data points should we label next, or which labels should we get next to update the model or to learn a new model? And in this case, we lose this assumption of IID among the data points, because we now control how data is acquired, okay? And this makes that we might learn faster with less samples, because the samples are optimized towards maybe the decision boundary. Okay, so that's the first type of learning curve, mostly the one that we see in the lectures, but probably not the one that is mostly used nowadays, which is an iteration-based learning curve, as we can see them, for example, in neural networks. So here we have curves that are a function not of 2 arguments, but of 3. So we still have a learner A, but now we have an additional argument, which is the second argument is still the training size. But we're not plotting the performance anymore in terms of a training set size, but in terms of iterations we spend on processing this batch size. That's an important separation between these two types that has only been superficially made until now in literature, but the two curves are really different. So here we could say we have the same neural network with the same hyperparameters, but we use different amounts of data. And then we get, for the same architecture, 2 different curves. And here we see N2 is probably higher than N1, so we can use more data. So the curve converges at some better performance value. And the relationship between the 2 curves is that basically the curve that we see on the first slide, the sample-based one, is showing what do these curves here assume in the limit as their values. Okay, so if we process them for an infinite number of iterations. So yeah, one might ask, okay, yeah, but why do we have to make this separation? In the end, they look somehow similar. If we want to fit a model on them, we will probably do the same. So what's the matter? Well, here in this idealized plot, they indeed look the same, but it turns out that we observe now phenomena like a double descent, for example, and everybody talked about double descent and the problems that come along with double descent for modeling learning curves. But does double descent occur at the same rate for iteration learning curves and for sample-based? And the answer is no. So that means that depending on what we want to model and what assumptions we make on the modeling process, it would be good to know and to understand which kind of learning curve. Okay, so I think we will delay the update. So here's another one, very interesting. So oftentimes we only focus on generalization performance. So what's the accuracy of our model? But in fact, data has a cost. We all know that data has a cost in acquisition. So what people have looked at very sparsely, to be honest, is also the utility of a learner or a model. So you don't only ask for, okay, so what's the performance in the number of samples or in the number of iterations, but also what's your utility in that? So you can say, okay, if I get 100 or 1,000 instances more, I will improve my accuracy by 0.1 or 0.01, for example. But the cost that is incurred by this acquisition of this data, does it really justify or the other way around? So the accuracy or the improvement in the performance measure, does it justify the costs incurred by them? And this can be measured through utility functions. Yeah. So here one would say this curve hasn't even converged here, or barely at this point. But we see that really in economic terms, we wouldn't want to go there. We don't want to acquire so many instances. We want to be somewhere like here. Not go for the last percentage in accuracy or even the point after the 2 positions after the comma, but go for something that is reasonable in economic terms, in terms of utility. So Jan will also go a bit deeper into this in the third part. And there's also other kinds of performance curves. I'm not going to talk about all of them, but maybe just 2. So one interesting concept is feature curves, where you have also on this axis here, so it's always for example, here it's the error rate, but whatever measure on the y-axis, and here you have the number of features. And now it depends, of course, a lot on how many samples you have. So if you have some fixed number of S samples available, then, well, your performance, we all know that the performance will behave somehow accordingly to the number of features. If we have very few features that are not informative, we will not have such a great performance. Getting some more informative features will improve the situation. So we have this slope that goes down here. But then if you have, again, too many features, then the learner will be confused and the performance will start to deteriorate again, okay? So if we have an infinite number of samples, then this won't happen and more features will just be helpful. The interesting point about this one is I don't have the time to go into too much depth here, but in fact, this curve doesn't really exist in this sense because features are not IID, such as instances are. Yeah. So if you just get the next right feature that is perfectly informative, this curve will drop immediately and you're done. But maybe this feature doesn't even exist. So this curve somehow is pointing to an idea that maybe more features can help, but it's not always clear whether these features really exist and how which features you would take to evaluate the performance of a learner at which point of time. Okay, so it's a delicate topic. There's not much publication. There are not many publications on this topic, but it has been there. I think it's been around for almost 20 years, sparsely examined, but could be also very interesting. And capacity curves, similarly, model the generalization performance as a function of the model capacity. So this is something, we can think of a random forest. This could be the number of trees in a random forest, could be the capacity of a neural network, for example. And again, for a fixed number of samples, typically if we increase the model capacity, we increase the variance of the learner in the base variance spectrum, we can at first improve a bit, but then again, somehow the model complexity becomes too large and the performance will deteriorate again. Again, if we have an infinite number of samples, then we don't have this problem, but not necessarily does this curve converge to 0. So this here is what one of the pioneers in learning curves, Corina Cortes, called the intrinsic noise of the data. So so if you don't have the appropriate features in your data, no matter how able your model will be, you cannot improve over the intrinsic noise of the data. So this does not necessarily go to 0 here. Okay, so one problem with learning curves is that we don't know them. So we all know that the out-of-sample error, even of a single model at a single point, cannot be computed. This is because we don't know the probability distribution behind it and so on. And of course, then much less are we able to compute this expected value. It's entirely out of range. So we can draw them somehow as a concept, but really we don't know them. So this brings us to empirical learning curves. We have somehow to estimate them. And the remedy is as usual. So we estimate the curves based on some concrete set of data we have available. We build train sets, validation sets, and then we estimate them somehow pointwise, right? And these points S, where we do this is what we refer to as anchors. These are the anchor points, which we use somehow to have some orientation about how the learning curve looks like. And fair enough, there are publications, or there have been publications from the 90s on that do nothing else than report empirical learning curves. Yeah. So, for example, here I'm citing one paper of Claudia Perlich in 2003. They do nothing else than reporting empirical learning curves of logistic regression and decision trees in order to compare them. And this already indicates that they are somehow valuable resources, right? Because we somehow want to understand more about learning curves, but how can we do that if we don't have empirical learning curves, which are, so to say, our window to this concept? And there are two resources that I would like to recommend to you. The first one is LCDB. That's the Learning Curve Database. That's a publication we have at ECML this year, also together with Jan and two colleagues from the Netherlands. So what we did here is that we provide an API access to learning curves on accuracy, error rate, F1, log loss, or basically we have the prediction vectors for 40 learners on 240 data sets. Available. That's a fairly large database. I think it's like 200 gigabytes or something like that. We have 10 train validation test folds. So basically you can use this to instantly query sample-wise learning curves. So learning curves of the first type we saw. There's another one, and this is by margin, the largest database that is currently available for this type of learning curves. There's the second one, LC Bench, that has been published by Marius and one of his PhD student co-workers, I guess. This is a database for learning curves based on iterations. So it stores the iteration learning curves of 50 episodes for 2,000 architectures. Not sure whether hyperparameters are included there, on 35 data sets. So to my knowledge, this is the best resources you have available if you want to work with learning curves without evaluating weeks on your cluster for getting these insights. So if you're interested, you can check the GitHub repositories or just come to us later. So this is a figure that will come back a couple of times today. I'm not going to go into it too deep, just explaining at this point of time one concept here. So the idea of a learning curve is now clear, I guess. So we have this descending. So here it's always in terms of error rate. If it's not that we cite the figure of some paper, it's always descending curves as a function of something, as a function of the data set size or as a number of iterations. So these are the anchors here. And the concept I want to point up here is the one of the saturation points. So at some point, these curves will converge, which is here the red line. The red line shows the limit performance. So what's the performance you get in the limit if you had infinite number of samples or an infinite number of time steps, iterations available? Yeah. But often we don't get there. So before that point, there's what we call a saturation point. That's the point where the performance will increase so marginally that you can even neglect it. And so that's a user-defined threshold. You say you define some epsilon. You say from that point on, where performance will, within a certain range of samples or iterations, only improve upon some epsilon. You say the curve is saturated. You could theoretically also improve, but yeah, so that's out of range. Okay, so that's the saturation. So the saturation point is the number of samples or the number of iterations where this happens, and the saturation performance is the performance observed at that point of time or at that number of samples. Okay. And somehow intuitively, that's a reasonable point to go. There's also another one, which is the pre-exponential point. So before the saturation point, you have this kind of kink here in this curve where you say, okay, even before the saturation point, it could be reasonable somehow to drop the learning process or to stop the learning process, because say, okay, yeah, I can still improve even more than some epsilon, but the effort I have to go is so big that it's not worth the pain. That also goes strongly into this direction of utilities, right? Okay, so but that's the saturation point. So ideally, one concept or one property we would like to have been fulfilled by learning curves would be monotonicity and convexity. This is what is often referred to as well-behavedness of learning curves. So monotonicity is clear. It just says once you obtain some improvement with your learner, you won't lose this improvement. So it's only getting better over time. The problem is that you can somehow, if you only have monotonicity, then maybe your curve always improves, or at least doesn't get worse, but maybe at an irregular rate. And that can make it a bit hard to make predictions about how is learning going to evolve over time for this learner. Convexity gives you precisely this. Convexity introduces a notion of, let's say, regularity in this process, makes that you have a monotonistically decreasing gain in the performance. Okay, and it's precisely the convexity that gives us these nice curves. If it's only convex but not monotonic, it could go up afterwards, after a time, right? So it's the combination of monotonicity and convexity that gives these nice shapes of learning curves. And now one can ask, okay, yeah, it's nice to make this kind of assumption, but is this assumption satisfied in practice? And the answer is yes and no. Yes, with respect to sample-wise learning curves. So you can assume somehow that learning curves that are based on samples will almost always look somehow like this. Okay, and we could verify this empirically based, so there are even theoretical results on this. But we could also empirically verify that this is the case in the LCDB. Now you can ask, okay, where's the double descent here? So for those of you who are not familiar with the double descent phenomenon, this is like you have a peak here. So you're improving in terms of your error rate, then you deteriorate, and then you improve again. So you would have something like a peak in this curve, or even several peaks. Yeah. So if we claim here that learning curves are well behaved, what we are saying is that double descent does not exist. And the claim goes certainly into such a direction that double descent does not exist for sample or observation learning curves. It does, however, apparently exist for iteration learning curves. Yeah. So we did not check LC bench with respect to this yet, but probably one would be able to observe, at least on some data sets, that you do not have this type of well-behavedness of the learning curves. And that's an important observation, because that means that if you want to model a learning curve, and we will now see how we can do this, then whether this model is appropriate or not depends really a lot on whether you model a observation learning curve of the first type we saw, or an iteration learning curve where you do not have maybe a theoretical justification for using that the model classes that are typically used for learning curves, that are all somehow of this shape. So we are not aware of any function class that appropriately that properly can handle these peaks. And that's a problem if you want to, for example, extrapolate observations in a neural network that starts off with a learning curve that has these peaks. So there's a lot of work to be done in this respect, I guess. So talking about modeling learning curves, then how can we do this? So what's the objective of modeling a learning curve? Basically, going 2 slides back, is to get to this curve just from some observations, right? So we want to understand how the learning process is working. So get to a true learning curve, or model for the true learning curve from some empirical observations. And to understand how this is being done, so first it's important to understand that the empirical learning curve itself is like the result of a stochastic process in which you are sampling from performance estimates at different anchor points. Because as we know, once more, what's the learning curve? It's saying what's the out of sample performance at some training size or at some iteration size, but we know that we cannot compute this. So we must sample this. So this introduces stochasticity. And more particularly here, it's what, I don't really know who introduced that, whether it was Aaron Klein, but I think I read that the first time in his publication. So he called this heteroscedastic noise, which means that the noise you observe, so going 2 slides back here again to this figure, basically when you make observations, you don't have observations always on this line, but you have them even if you make observations at one point, like here, you get observations above the line and below the line. This is just what happens in a cross-validation. You say, I'm taking 100 or 1,000 instances for training, but you don't do this just once, but 10 times. Training 10 times on 1,000 data points, sampled independently, and then computing the some performance on the validation set. Well, then you get 10 observations, and not all the 10 observations will be exactly on this line, right? So you have some variance in these observations. And how big is this variance? So this variance is basically this term here, the sigma squared S, but I introduce this subscript of S here to indicate that this noise, this level of noise, depends on how many samples you use for training. It's clear that if you train a neural network on, let's say, 10 examples, then the variance in the let's say in the accuracy later on is much bigger than if you use 10,000 images, because the training batch is much more stable and less vulnerable to which instances eventually ended up in the training fold. So the noise you have for the empirical learning curve is higher in the beginnings of the learning curves and lower in the end. Okay. So this is the noise that we have to consider when we observe, make empirical observations on the learning curve. And then what is typically assumed, with some reason I would say, is that these empirical learning curves that we can sample from the data are somehow following a Gaussian distribution, which says, well, the center of this distribution is the true value. Well, we should have an unbiased estimator of the learning curve as it is, but there's some noise, and this noise is precisely this noise I've been talking about, and this is, so to say, the model, and we can write this also as just, you say, that's the true value of the learning curve plus some noise that is centered around 0 with this variance here. Okay. So in the idealized figure on the first slide, we only have this here. So this is basically this idealized curve. So this one here, this is just the mean curve. But around this, and we will get, by the law of large numbers, we will get samples that center around this curve. And the empirical mean will also converge towards this value, but we have some noise around this, right? So the simplest thing we could now do would be to, if we want to understand and model the learning curve, the simplest thing would be to just model this mean itself, right? So we could just try to estimate this mean, mu S, for each anchor S, or for each possible point, and just ignore the noise for a moment, right? So how could we do this? There is really a bunch of models that is used for this purpose. One of the most commonly and first used models is the so-called inverse power law. That has been introduced, I think, in '93 by Corinna Cortes. So what it does is to say, okay, we have 3 parameters, alpha, beta, and gamma. All of them are non-negative integers, real numbers, sorry. And we model the mean at any possible point of the curve by saying we have some alpha plus beta s to the minus gamma. Alpha is basically the limit performance. This is how good your model can get with an infinite number of samples. Okay. And these two here, so alpha basically controls the plateau, and beta and gamma somehow control the rest of the shape of the curve. Okay, so but that's one model. A lot of others have been introduced over the last years. Jan will have a more complete overview of them. If you're interested in general in the topic of shapes of learning curves, I would like to recommend the survey by Tom Wierig and Marco Loch. That was it's also an archive paper that has been uploaded to archive this year. It's a fairly complete and comprehensive overview for this topic of shapes of learning curves. It's called like that, the shape of learning curves. So, but this is just to have an idea how we can do this. So here we are ignoring the noise, and what we then would like to do is, in this case, we have three parameters. Alpha. So here we have three parameters: alpha, beta, and gamma. So, and the goal is then, or we have an inference problem that says, okay, we have the inverse power law or the some other model. There are empirically better models than the IPL. So I'm just using it here because it's the most known model, but it's certainly not the best one. In any case, we have some set of parameters that can describe this curve model. I call them here beta 1 to beta m, and they describe the behavior of the mean. They are not describing anything of the noise that we have in the observation. And the center of our attention is the probability distribution, or just the likelihood. So what's the likelihood of these parameters given D? And what's D here? D is not the data set that we have available for training. D is basically the empirical learning curve. So D is saying we have for different anchors, different performance estimates or observations. So this has nothing to do with the original data XY that was used to train the model. Okay, that's important to make this separation. So D is the empirical learning curve, so to say. Which performances did we observe with some validation technique? Can be a hold technique or can be cross-validation technique on some anchors. And then for a point-wise model, if we're just interested in one curve, then what we ask for is, well, the maximum likelihood estimator, which is just the argmax of that expression up there, right? So which are the parameters that are most likely to well describe the mean, the learning curve? And this, so if we look at this function here on the last slide, in the case of the inverse power law, we can see this is basically a non-linear regression problem, and you can solve it with any non-linear regression algorithm, like, for example, Liebenberg-Marquardt, or this is one that we used a lot, but you can also use others. Sounds almost trivial. We found that for some models, it's quite tricky to converge to good solutions. So this can be a bit nasty, these formulas, and you can run into numerical problems. But in general, it's just a regression problem, and we know that the solution to this regression, the optimal solution to the regression problem, is the maximum likelihood estimator that will model us the, so to say, the single best curve that describes this learning behavior. Okay, but now there's an interesting twist, because we could say, okay, wait a moment, what's the best fit? So let's suppose, going back again to this figure here, let's suppose we have not yet arrived at this point. Let's say that we are here at this vertical yellow line. So, and we have made some observations. So imagine that we had a scatter plot here where we have made some observations up to this point. Then what a regression model does is to build a curve that best matches the data points in this window. But this is probably not what we want. What we want is to somehow predict how this curve will evolve, and to which of, maybe if we have several learners, we want to know from several learners how will these learning curves evolve over time, and which one will then be best. So in regression, we only look into the window of data points we already have. But for learning curves, we are often, specifically in the context of model selection, interested in how do these curves evolve after our evaluations. Okay, so there seems to be an inherent problem, and what this has been already pointed out 20 years ago by Gu et al. So here. So if our goal is only to explain how the learning curve looks, well, in this range of observations we have made so far, a regression would be the best thing to do. But it has been shown empirically, and quite convincingly, I would say, that the solution you get in this way is not properly telling you how the learning curves will evolve after the window that you have observed so far. So that means that this regression approach is not a good solution for the extrapolation problem. And as far as I know, this is somehow an open problem. I'm not aware that anybody has come up with a formally proper definition of how you can, I mean, it's probably too hard to do it, but it just hasn't been done so far, of how you can pose this extrapolation problem in a sample, okay? So if you still are looking for a topic, that could be something. So what you will observe typically is that if you come up with these parameters that best explain the learning curve up to here, you will most probably have a suboptimal prognostic of the learning curve, which means that you might pick the wrong algorithm. If you have, let's say, 10 algorithms, you have observed them up to a sample size of 1,000, but you have 10,000 samples to go. Maybe your extrapolation or the model that you get with the regression is then suggesting a model that is indeed suboptimal. Good. So, but up to this point, we have only talked about well, estimating this single curve. Where's the uncertainty? We somehow should be uncertain about our model. So this came later. That came up, I think, in the 2003. 2003, I think, is the first paper where they started to introduce uncertainty about these curves. So the first question should be, what are we uncertain about? Because when we did this literature review, I was sometimes wondering, okay, we're now modeling uncertainty about what? Because there's a lot of things you can be uncertain about. The first thing is that, okay, once you get a model, so let's go again back to our figure that will pop up a lot. I already said it. So once we get such a curve like this and we make a prediction here, for example, at this point, we could ask, okay, what's our certainty that this value that we're predicting with this curve is the correct one? This is something that, if you're familiar with Gaussian processes, you can express, for example, with Gaussian process. Yeah. So this uncertainty. So that could be one uncertainty, or the other way around. What's our certainty that the prediction is correct? Certainty. However, the second one is, okay, so we're doing. We're estimating parameter values. So we could also ask, what's our certainty or uncertainty about the optimality of our estimates with respect to the data that we've seen? Okay, how sure are we that so we're committing, for example, to a specific model class, like the inverse power law, 3 parameters. We're estimating some single curve based on some data. What's our uncertainty or certainty about that these 3 parameters are really the best ones for the data that could be generally available? Yeah. So it's the question, how comfortable do I feel, or how sure am I that within the model class that is subject to a discussion, we already identified the best one or the most correct one with respect to the true learning curve. And last but not least, we could also be uncertain about whether our model class is at all appropriate for doing this, because you can see, for the case of inverse power law, that there are a lot of learning curves that are not properly modeled by the inverse power law. So one should think, maybe we should not use an inverse power law. So that's a common issue, obviously, in statistics. You beforehand commit to a specific model class and then say, okay, I'm looking for the most plausible model within this class, but whoever said that this class is sensible for this particular problem? So that could also be something that you're uncertain about. and maybe other things. But these are at least three suggestions. So in this context, it's sensible to recall the concept of aleatoric and epistemic uncertainty. So for those of you not familiar with these concepts, aleatoric uncertainty generally refers to randomness in the signal, which is, so to say, inherent to the problem. It's uncertainty that you cannot avoid. So the dice that you roll has some stochastic result, and you cannot get rid of that. It's just part of the nature of the dice. On the other hand, there is also epistemic uncertainty, which just means that maybe there is not even randomness. It's just that I have insufficient information to be sure about what the condition of some system is. So these are two inherently different motivations for using probability to model some uncertain condition, but the reason why we're using probability is different in the two cases. And why we cannot get rid of the aleatoric uncertainty, because it's just part of the nature, we can reduce epistemic uncertainty by just informing ourselves better, by acquiring more samples, for example. So the latter one is similar, or both. You can, for example, if you're familiar with Gaussian processes, that's a concept where you can find both. Yeah. So you can have noise at a specific point. So when you inquire a particular point several times, you get different results, and this difference in the results is based to the is thanks to the aleatoric uncertainty. But you also, for some other points where you have no observations, you are just unsure, you have a belief about what the value of the function in this region is, but you really are not so sure about it. But that's because you have not observed samples in that area. And this is expressed through epistemic uncertainty, okay? So, in the case of parameter fitting, what we are uncertain about in the epistemic case is the correctness of the values of these betas, because we have maybe not seen enough samples. Yeah? So we would somehow maybe like to express our uncertainty about these estimates. So there are in literature two approaches, and we'll go into a bit more depth on this, but the first one is the range estimates. So range estimates somehow define lower and upper bounds for the estimate of the mean value. So you have some mean value, which is the single curve, and then you create some bands around these around the single curve. And when it says lower and upper bound, it's not really referring to infimum or supremum of the possible values, but it's just some sort of characterization of this uncertainty. Some have used confidence intervals. Others have used simply Q1, Q3. Yeah? So you build the interquartile range, and this is your band that you draw around this curve. And this is not necessarily, but in fact, in literature, it's just used to address the aleatoric uncertainty. So you say, yeah, okay, I believe that the true mean value is somewhere in this range, and you quantify the uncertainty of this, the aleatoric uncertainty by this band. Okay, how useful is this? Well, this is. I think that depends a bit on the application. You have to ask yourself, going back to this one here, you have to ask yourself, is the aleatoric uncertainty important to you? So is it for you important to understand the noise that you have in the data? Then, of course, that's it's somehow important to measure this or to assess this. If you don't care about this, you just you don't care about the noise you have in the samples, then this may be not the way to go. So that's range estimates. So here we're going from point estimates to range estimates, strictly more, right? Before we just had a curve. In range estimates, we have a curve plus bands. The third degree is distribution estimates, because where does the mean come from? Well, the mean is the mean of some distribution, right? And where do ranges come from? Well, it's also either a confidence interval or some statistics that's defined over a distribution. So it's somehow sensible to say, yeah, why don't we estimate the whole distribution right away? So we could say, we already talked about, we are interested in this likelihood of these parameters given the empirical learning curve D. Yeah? What does this, by the way, do? In fact, this is nothing else than the characterization of the empirical, of the epistemic uncertainty. Because if we are absolutely certain about how this mean looks like, then this here will be a direct distribution that assigns probability 1 to exactly one configuration and 0 to everything else. If you're uncertain about the correct parameters, so that means that you can still conceive different learning curve behaviors as reasonable, well, then you will not have a direct distribution, but something a bit more general. Most often modeled as a Gaussian, as we shall see. So this is really saying nothing else. If we are modeling this likelihood directly, we're directly assessing the epistemic uncertainty about our estimates. So, okay, how do we get there? How can we do this? This is not anymore by maximum likelihood estimation, because maximum likelihood estimation was just taking or getting us the argmax of this expression. Now we somehow have to do something else and get this posterior distribution here. And as we all know, this is a tough problem. Bayesian theorem gives us that this probability here is proportional to the probability of observing our empirical learning curves, given that the true parameters would be like this, multiplied with the prior. And even this here is intractable. Yeah, so everybody knows, okay, we can't get here, but there's this nice trick that we can sample from this distribution here. So if we know this here, we can quantify this here, for example, based on some assumptions that at each point on the curve, the observations behave like a Gaussian. This is something we already did assume before. Here we can also put some prior information or incorporate expert knowledge. And then once we have it, we can sample, for example, using Monte Carlo Markov chains to estimate this probability. And I will also explain in a second, once we did that, how we then can use this information. So in this case, once more, the aleatoric uncertainty, so the noise that you get when you sample from the learning curve in your empirical, so the noise in your empirical learning curve, this is not considered here in the formal model. But that doesn't mean that it's not important. In fact, if you know, or knowing this aleatoric, or having at least an estimate of the aleatoric uncertainty, can also be important for estimating or for having an idea of how you should model this here. Because, I mean, intuitively, this is probably clear. If you say that I'm observing a very high variance, so let's say the accuracy of my learner depends a lot on this concrete split that I've been taking, then probably the information is not so reliable. So this D here is somehow noisy, and I can not use it with the same confidence as if I had very low variance, okay? I'm not aware that this is done currently by anybody, but I think it's a quite interesting aspect of this problem, taking into account the aleatoric uncertainty to assess the certainty about, so it's somehow kind of a meta certainty on a meta level that our estimation process here is going well. Yeah? Okay, so let's suppose that we can draw some samples here from this distribution. How is that then useful? Well, let's say that we have capital S many samples drawn from this posterior distribution with MCMC, for example. Then, so these samples give us samples of these parameters, beta 1 until beta m, right? So if we have them, then we have basically capital S many descriptions of different learning curves, or capital S many learning curve models. And now for each of them, we can ask for a concrete point, for a concrete anchor, minor s, what's the performance according to that model at that point. And if you ask all of the capital S many models, you get these scores, and you can form just the mean over them. It's just like you query opinions, right? And every ZI is an opinion of a different learning curve model at minor s. You average over them, and that gives you an estimate of the mean value of the learning curve at the point S, according to your belief model. And this is why it says this P in the subscript here. Now, if you have this mu, I mean, we had this before. We already had a mean before with a maximum likelihood estimator, but now we can use this mean here to compute the second order momentum in the variance. So we use this value here and put it on the right, and also compute the variance. So that's, so to say, quantifying the uncertainty of our model. It's the variance that our estimators do have for this point. And we haven't really gotten to a complete model of P yet. We only have a mean of P, and we have a variance of P. How can that be useful? Well, that can be useful if you make, for example, the assumption that P is a Gaussian. Because if P is a Gaussian, then you only need the mean and the variance to describe it, right? So this is what is typically done. In fact, that's one of the approaches that is pursued here by Aaron and Frank in their Bayesian neural networks that Jan will also explain in a minute. And so by applying MCMC for getting these samples, you get a belief model over this distribution. So basically with this, and so combining that you have a mean and a variance, and assuming that this thing here is Gaussian, you have a full description of this probability of this posterior. And this is, for example, useful if you want to say, okay, we are comparing different models. And now I want to ask, what's the probability? How conceivable is it that model B will still outrun model A in the long run? This is what you will use then this posterior probability for. But this, I'm going to explain this now, what the use cases of this are. So, but these are basically the three types of models that are typically used. Only a pointwise one, just estimate the mean itself, but that doesn't include any model of uncertainty. The second one is a range estimate model plus confidence bands. And the last one is, give me the whole distribution over learning curves that reflect your belief. And this is, for example, this can be done with MCMC. Up to now, it's, I guess, the only approach I've seen to solve this problem. Okay, so that was the first part as on the background on learning curves. I hope that you learned something new about learning curves at this point. So how do we now use this for decision making? So we identified three main use cases. If you have any more, we're really curious and interested in learning more about that as well. So, but we have identified three types of decision situations where you want to make use of learning curves. So the first one is data acquisition. I already said that. So the acquisition of how many additional labels is economically reasonable. And here with this economically, I'm emphasizing once more that it's not only about maximizing accuracy in the long end, but about maximizing utility. So one additional point that will be explained by Jan. Second one is early stopping. And early discarding. So I'm already explaining here the difference. This is a distinction that we introduced because we felt that the concepts are often somehow mixed up. So what we refer to as early stopping is that you say, okay, you have one model like a neural network, and you're training this, and you want to recognize in this training process some kind of convergence that you can stop this. So maybe you set some parameter of maximum number of iterations, but you don't want to run the whole number of max iterations if not necessary. So try to use a learning curve to detect early that this has already converged, even though we are still far away from max iter. Everybody is, I guess, aware of this the problem. And the third one is what we call early discarding. So here, this is now the model selection process, and you want to say that you stop the training procedure as soon as you can recognize that a candidate is not competitive anymore. So going into each of them, because each of these three cases has some maybe caveats that are worthwhile to be discussed quickly. So for a single learner, you can create this learning curves, for example, based on, not for example, in this case, it's really based on the number of samples. It's not iteration-based learning curve. If you are talking about data acquisition, it must be what we call type 1 learning curves, the ones based on number of samples, not iteration-based learning curves, because that would just not tell you anything. Okay, but that only tells you maybe, okay, this converges at some point. Maybe it already converged at the number of samples you have available. That only tells you whether you can improve the performance of that single learner with more instances. That's not the question that data scientists typically ask, or let's say practitioners maybe. So what they ask is, if I get more data, can I eventually get better with any model? Or can I get an improvement? Can I improve the performance of the currently best learner by adding more samples? And there could be another learner that is currently not optimal, but if I give it more data, then it will take the lead on this additional data and will improve the overall performance of what we call a portfolio. So you define a set of ensemble of learners, and you ask, can you improve by additional data points the performance of the currently best by any model? It can be that that model improves or another model improves over the one that is currently the best one. Yeah? And that is very similar to what we saw in the beginning with these capacity curves, because you can say that you have some kind of portfolio with learners of different capacities. Some are more able or have a high variance than others, and adding more data can lift one of the learners up to take the lead on more data points. Okay, so that's with respect to the first one. It's important to have that in mind, that it's not really talking about a single learner, but somehow about a portfolio of learners. And yeah, I think one can already see that it's maybe not so trivial. So if this portfolio is maybe infinite, yeah, because the portfolio consists of all hyperparameter configurations of some learner, then the question is, okay, how can you possibly know that there exists any architecture or any hyperparameter configuration that could not benefit or enjoy additional instances to eventually improve over the current state of the art, right? So it sounds kind of trivial, but yeah, probably it's not so easy in every situation. I think this is a fairly underestimated topic currently. So maybe it's also a bit difficult to get a grasp on this scientifically. My experience in practice is that this is one of the most common problems you face, yeah, because people have to decide, okay, we already have some data, do we need to get more? And that's the question they really have. They have to invest time and money to get these additional instances. And oftentimes this is not very well addressed. And I think it's a great opportunity for the AutoML community to seek how can AutoML tools support this question. Can AutoML tools create learning curves? So we have some approaches that are able to do that. Replace tenfold cross-validation by what we call a learning curve-based cross-validation. Jan will talk about this. You create learning curves. Can you use that resource that you create with AutoML on the fly to support the user in this question? So second one was early stopping. I'm going to be really brief on this one. So this is what you know from neural networks. For example, you can separate some validation fold that has never been looked at during training, and that this one you use to create a learning curve. And when you see that this learning curve on the validation data stalls, then you can stop the training process because you know that you have converged You can even avoid overfitting by doing this, right? So that's early stopping. The important notion here is there's no kind of comparison. It's just looking at that model itself. It's not asking for any baseline, anything like this. Just observing the learning process in isolation of this learner. Can we say that we have converged or not? And if so, let's stop the learning process. And that's different from early discarding, where we say, okay, we have some sequential process in which we do try to find the best model among some predefined set. And we have some baseline tau, and this baseline is updated over time. So tau is basically just the best performance that you have observed until some point of time, right? So what is that, by the way? Typically, that means that you're talking about a concrete point on a learning curve. You say, I have 1,000 instances available. I want to use 100 for testing. So what I refer to as a best solution is that learner that if using 900 instances for training gives me the best model. That's not necessarily the best learner when if you have only 800 instances available. So only the decision on do I do my test my testing at the end with 10% of the data or 20% of the data. Only this decision can already change which solution would be better. So that's often treated implicitly, but probably it's good also to have that a bit on the screen. And then with respect to this early discarding, it's worthwhile to separate different types of algorithms that make different kinds of assumptions about how they do this model selection process. So we're mainly separating here two groups, which we call horizontal and vertical model selection. What does this mean? So horizontal model selection means to us that you have a fixed portfolio of learners and then you grow their learning curve simultaneously from the left to the right, meaning increasing data set sizes. It's what often is referred to as multi-fidelity optimization or, yeah, exactly. So this is above all what is done by successive halving. You say, I have maybe 100 learners and I'm first training all of them on only 5% of the data. Then I'm picking the 50% that were best on this small portion of the data, and they keep growing their learning curves. So you have 100 learning curves that are grown from left to right, but at each point of time, you drop half of the learners or some portion of the learners and say they are not competitive anymore. I'm ignoring them from that point on. So this is why we call it horizontal, because it has a process that goes somehow like this, if you would visualize this. In the vertical case, it's different. Here, you don't know the portfolio of learners in advance. You just say, I have somehow a process that receives candidates or looks at candidates, and then it builds for each of them when it's turned for this learner. It builds at that moment the learning curve and then tries to discard the candidate as early as possible. This is what we do in learning curve-based cross-validation, and it does not assume that you know in advance which learners are considered. And there is many approaches follow some kind of hybrid strategy. So they take somehow a horizontal approach, but they allow that the portfolio that is grown or whose learning curves are grown can be adjusted over time. So for example, if you take hyperband is nothing else than successive halving in the first place, but you say after each iteration, you allow to adjust the portfolio a bit. You can add new learners to it. So this is combining somehow the ideas of both. It's also the case in freestore, Bayesian optimization, and fabulas, and other approaches that Jan will be talking about now. So I think I will not talk about this figure because Jan has it as well. Maybe just one comment. So there are many questions you can make about learning curves. You can ask, where is the saturation point? What is the limit performance? Will learner A eventually get better than B? You cannot, but okay, for example, taking these questions, you do not necessarily need a learning curve model. So you observe an empirical learning curve of learner A and B, and you can just with this answer the question, will A take over B in the end? Yes or no? You do not need to model the learning curves to do that. What is often done is that one solves a more complicated problem, because modeling a learning curve is a much more difficult problem than only asking a yes-no question. But often this is done so one solves the more complicated problem of fitting a whole learning curve, maybe with a probabilistic model, only to then answer a binary question in the end. That's one aspect here which we found interesting, that often simple questions are answered by solving, in the first place, more complicated model or more complicated approach. It's reasonable, because if I want to know whether A will be better than B in the end, it's reasonable to say, let's examine how they will evolve in the end. But maybe it's not necessary. Maybe we can just have a binary classifier that will tell yes or no, just based on the empirical observations. So I think that this is also interesting for future work, then that one looks, okay, often we are only interested in very simple questions that are up here. Do we have to make all the way down here to answer them, or can we have more direct approaches? Yeah. And eventually, so what are the resources we have available? So, of course, we have some empirical learning curves on the data set that we are examining, but maybe we have for the same learners. So let's say we are comparing logistic regression with a support vector machine. So maybe we have for the same learners also empirical learning curves on other data sets. If you have never observed that a learning curve of a perceptron, if you have never observed that the learning curve of a perceptron outperforms the learning curve of a random forest, and probably you have not observed that, then why would you ever consider the possibility that a perceptron will outperform the random forest? So this is using learning curves on other data sets for this inference problem. On the other hand, you can also say I have a fixed data set, but several, for example, neural network architectures. So I have seen on the same data set already how other neural networks behave in terms of learning curves. How can I now use this to extrapolate the learning curves of new neural network architectures on the same data set? So this is just to show that there are really a lot of conditions to take into account if you do this kind of studies, and it's really worthwhile to consider different possibilities of resources that you have at your disposition. Do you have dataset meta features maybe, or learner meta features that describe how your learner is behaving, all this kind of stuff. So, and with this, I hand over to Jan, but no worries, it's not a 50-50 talk. So. For the literature review.
Yes, thank you very much, Felix. And this comprehensive overview, of course, helps me in doing things a little bit faster in the second part. And I will be very mindful of time and lunch, so don't worry about that. Good. So this image, Felix already kind of showed the most important part, namely that quite often, we want to answer a very simple question. Is the performance at a certain of this learner at a certain data sample, is it better than some reference? That's what we do in Bayesian optimization, of course. That's the simple question, but quite often we do more complicated things where we completely model the learning curves. And basically that's how we also structured this literature review, how I will go over it today. There's these simple binary questions. We found no literature. Of course, we did find literature that answered those binary questions, but no literature that utilized only the binary question. And this is how we kind of will structure this. If a technique used a more complicated technique to answer a more complicated question, this is how we will categorize it. So then we will start with value-based questions, basically a question: what is the saturation performance of a certain method of a certain learner? And basically that's of course a regression problem. More complicated questions could be the modeling the whole curve of an entire learner. That's what we will go after that. And then basically you go into the realm of the inverse power law, for example, on early points. And finally, what you can do is you can go beyond a certain learner. And I think there are some very cool methods that actually try to learn across learners. How do the learning curves evolve? Now let's go quickly into this. First of all, the identification of saturation performance. So given a certain learner, what will be in the limit, given the maximum amount of data that this learner can learn with, what will be the performance of this? And in case of observation-based learning curves, of course, then the use case is data acquisition. How much data do I want to sample in this case? And in iteration-based learning curves, basically then the question is how much epochs do I want to invest into this project problem? And this is actually a very interesting problem studied also from a theoretical perspective, because these curves converge quietly in a nice way. But one of the interesting insights that Cortez et al. Reported in 1994 is that there's some certain symmetrical behavior between the train curve and the validation curve. And kind of I picked this image from another paper. So, but kind of the idea is the same here. We have here on the x-axis the number of observations, and on the y-axis the performance in terms of error rate. So lower is better here. And we see here something very typical for learning curves, namely that given more data, of course, the performance on the test set gets better, but also what Cortez et al. Report, given more samples on the train set, and we will also get more noise in our train set. We will learn to regularize this noise. So given more data, slowly our train performance goes up. And basically the insight that Cortez et al. Used for this is, there's this symmetrical part and they probably meet somewhere in the middle. So the moment that the error on the train set increases, that's when they say, okay, we pick now the average between the validation performance and the train performance, and we assume that to be the saturation performance of a certain method. So that's one method of assessing the saturation performance. Let's go on to identification of the saturation point. And of course, here again, for the observation curve, you could say how much data do I want to utilize for solving this problem. And for iteration curve, there's a very obvious point where we want to say, of course, we want to use early stopping because we already obtained a certain performance. I'm going to skip quite fastly over this because I think most of you have, of course, already used iteration curves for early stopping, where you say, okay, the performance has not had. And there's, of course, a big difference here between iteration learning curves and observation learning curves. For iteration learning curves, basically, after every epoch, you can for free determine what was my performance. And then for every observation-based learning curve, it of course does not come for free. I will skip here over the iteration-based approaches because we've all seen and utilized them in the past. But for observation-based curves, then the most important thing is how do I actually sample those points? And you cannot do it at any data point. And the key insight here that's still used in modern techniques nowadays is here. What we want to use is a geometric schedule where you double basically every time the data when you want to sample a new point. And actually, Provost et al. Come with a dynamic programming technique that even does something better, that schedules the optimal schedule for you. But they also come with the proof that asymptotically, if you use this geometrical schedule, things will, in terms of runtime, never be asymptotically worse than this optimal schedule. And this is a proof that actually comes back every 2 years in some new paper. This is kind of reinvented. But this is basically some sort of a retrospective approach. At some point, we've created a learning curve and we determine at some point, okay, but we have now saturated. We probably should not continue moving in this, but can we also projectively determine this? Well, that's some work that was done in 2004 by Pavel Brasdeel and Rui Leijten. And basically, their aim is to, after already a certain amount of data samples, determine what is the saturation point of this specific learner. And basically what they need for this, or what they use for this, is So suppose that you have a certain learner on a certain data set and you want to know what is the saturation point. They basically also need learning curves on previous data sets of this exact same learner. And basically then based on those data points, they employ a KNN-based model to determine which of the learning curves on similar data sets look similar to the current learning curve. And the closest one can then be taken as, okay, where did this one saturate? And then this can be used. Also, they employed a geometrical schedule. And of course, since it's a KNN-based model, they can not just identify one closed data set, but they can identify several closely related data sets. And they experiment also with various ways to then aggregate what was the saturation point. It could be the mean, of course, it could be the median, and various other things. Good, let's move on to the utility-based stopping point. And the key insight for utility-based learning curves is kind of, what is the optimal amount of data or the optimal amount of resources that I want to invest into getting a certain performance. So basically, in saying it colloquially, what is the bang for the buck? How can I get most bang for current investment in what I do here? That's expressed here in a utility curve. And basically, what you're looking for then is this point on the utility curve, as Felix already explained quite nicely. But this is of course not easy to define because this is quite a subjective measure, right? What does a certain misclassification cost me? What does getting a new batch of data cost me? These are all things that need to be determined by the person using the method. But basically, one of the claims that Wijs and Tian in 2008 make is, well, you can combine all these costs into a certain metric. Of course, this has to be set then by the user. And once you've determined this utility function, then basically what you do is actually what Provost already did in his previous work. You keep on sampling progressively, and the moment that the utility curve starts to drop, this basically means that you that you overshoot your target, and basically that means that you're done and you don't want to continue any further. Yes, let's go to the next topic, performance bounding at fixed points. And here, to explain properly what is meant here, is basically, here again, we see a certain learning curve, and maybe what you want to do is determine what is eventually the performance at a certain point. But here we want to be a little bit more permissive in our statements that we want to make. So for example, what we want to say here is given a certain learner and a certain learning curve, for sure we know that this learning curve is never going to be better than a certain performance. And then why is this interesting? Well, maybe you've already observed a very good learner that obtains quite a good performance, and now you're actually starting with some other learner, and it turns out that it doesn't start super good, and eventually the learning curve does not evolve so well. So maybe you can already very early discard this. So in one sense, this problem is easier than the real problem that we're looking for, the regression of a certain performance at a certain point. But we might also have higher expectations for how correct our statement is. In terms of regression, we always know, well, it will be a little bit higher or lower. But in this case, we really want to be certain. If we say it's never going to be better than this, then we really want that it never is going to be better than this. This was first addressed by Sabrawal, but I'm going to skip a little bit over this because of the time. But they had one very nice insight, is that they also built upon the fact that learning curves most likely are convex, and basically they sample multiple points at different anchors, and basically what they can do is they can eventually extrapolate the learning curve in its most optimistic form. And basically, if this extrapolation does not does not improve over. Actually, what Sabrawal et al. Does is then they look at this most optimistic extrapolation, and then the curve that at the sample size of our current data set shows, in this case, the best potential performance. This is the one that we're going to allocate more data to, and they continue with this until a certain curve or a certain learner has obtained this final amount of data. Now, there are actually two disadvantages to this approach. One disadvantage is that it's not 100% clear that if one learner has obtained this final amount of data, that it really is also the best performance. And the other disadvantage is that we're here stuck with kind of the, as Felix explained, horizontal setting. So we're working with a portfolio of certain learners. And yeah, maybe afterwards we still have budget over. We can, of course, then run this whole procedure again with more curve. But of course, we maybe want to adjust this a little bit to something that is more flexible in the way that it handles these learning curves. That's actually some work that Felix and me did last year. Learning curve-based cross-validation, and learning curve-based cross-validation basically aims to make the how do you say, the cross-validation procedure a little bit more informative, and to help us with using a cross-validation procedure in a model selection context, because quite often we're running a certain internal cross-validation procedure, and we already see quite early that it's not going to look at anything good. Of course, you can kind of address this with successive halving or hyperbend, but those methods are in some cases quite, quite dismissive. Some, if half of the configurations will be dropped, but maybe if we look at the learning curve, we can already say, given the slope of the current learning curve, one of them might be dropped, but all the others we want to keep on and look at them until we know more, that we for sure are certain that these are not going to improve over the current work. And this basically builds upon the assumption that learning curves are convex. Here we see some examples of convex learning curves, which is something that luckily we quite often see with observation-based learning curves. And here we see some examples of non-convex learning curves, which are a little bit less common. Basically, here also we see an example of how this exactly works, and we again see here two curves fitted. Basically, here is the performance on our train data that we see slowly rises when we get more data points. Here we see the performance of our test data in orange. You use the mouse, which gets, of course, a little bit better, or error rate drops when we get more data. And basically we can now extrapolate based on the last two anchors what would be, given this convexity assumption, the most optimistic extrapolation that we would get if we would extrapolate this, given that the learning curve is convex. And here we see that would end up somewhere here. And maybe we've already observed a certain performance, reference performance on the earlier configuration that was better than this. So in this case, we know we absolutely don't want to continue this learning curve, because this most likely will be a waste of time, and therefore we don't do this. The other termination criterion is based on the train error, and if the train error is already higher than the best seen performance on validation error, then we also know this is not going to be good. So in this case, we also can drop a lot of methods early. I'm going to skip a little bit faster over some other slides, because I promised the organizers to not take too long. But basically, several works have explored how can we incorporate metadata, either metadata in the form of meta features, or metadata in the form of algorithm configuration features. And some very interesting works in this were done by Bowen Baker, who tries to model learning curves, not just based on the learning curve, but also on the hyperparameters. And this work was even further improved by Long et al., who found actually a quite nice way of describing a convolutional neural network beyond simple hyperparameters. It can of course be way more complex than just saying a network has a certain width and a certain depth, and Long et al. Use some very interesting way of describing this, and this obtained quite nice performances as well. So quick recap. So far we've only in this survey looked at the questions: what is the saturation performance? What is the saturation point? What is the saturation performance? And what is the performance at a certain point? But of course, as Felix already said, we can also model learning curves in a way more interesting way, namely look at how the entire learning curves evolves, and using that, maybe extrapolation will go a little bit better. And here, basically we can use models such as the inverse power law, several other models to determine and to try and fit earlier data points. And the main distinguishing factor here is indeed how to deal with uncertainty. Now then again, point estimates have been used as early as Cortes et al. Used already the point estimates of the inverse power law. John and Langley, they introduced a notion of probably close enough, but unfortunately they do not utilize this notion. But basically the main point is from the 1990s on, we already used learning curve models based on point estimates. A little bit more sophisticated is people that started using range estimates, and this can actually be as simple as having certain, having observed certain, how do you say it, samples at a certain anchor point, and then we are not just modeling the average curve, but we can also model basically the 25th percentile point at 75 percentile point, and that's basically what Mukarrier et al. Do. And most interestingly, and I'm going to skip the details for now, but this is the work of Domhan et al., where they also take into account the uncertainty about the model itself. And they basically do this for many learning curve models. Here we see some of the learning curve models that are proposed in literature and that seem to work reasonably fine, also used by Domhan et al. But basically this gives some idea of the type of models that can be used for describing learning curves. Quickly look at the time. Yes, then utility prediction at any point, and similar to predicting the learning curve, we can also predict the utility curve, basically by modeling the learning curve based on, for example, the inverse power law, and then typically also defining the cost curve, and then you can analytically determine what would be the optimal point somehow on this utility curve. Good, then actually I would like to skip to the conclusions, because I've promised the organizers not to go over time. Basically, most interesting learning curve models, please do talk to us about this offline. I think most promising or most interesting learning curve models are the models that not just model a single learning curves, but are able to generalize across learners with different hyperparameter configurations. And 3 examples that utilize this are freestar Bayesian optimization, Fabulous, and using learning curves with Bayesian neural networks. And then, sorry, these are really the most interesting figures. But, I'm going to skip over them. Basically, short summary of what we have done. Felix has given a formal definition about learning curves. I hope that with defining the iteration-based learning curves and the observation-based learning curves, that this gives more insight in what type of learning curves are we dealing with. The 3 decision situations that we talked about are data acquisition, early stopping, and early discarding. And basically one of the, I think, interesting parts about the learning curves is that you can answer, you can model various learning curve questions, and you can also answer various questions of increasing complexity, starting with the binary questions. Is this learner going to overtake a certain reference performance, going all the way to model the entire learning curve, which is then later also used to answer quite often either a binary question or a regression question. Which brings us also to some interesting questions for future work. One thing that I think is very interesting is which of these models is now the best. We speculated already a little bit about this, but there's currently no clear comparison between all these methods that utilize learning curves for example, early discarding or early stopping, and there's absolutely room for improvement. Many papers do answer a question that's harder than the decision situation. Can we actually utilize simple binary decision sets to answer those simpler binary questions? I would assume that there's absolutely potential there. And also none of the papers, actually, that's what I wanted to show at the left table here, but none of the papers that we analyzed, and actually what is hidden here in this table is that many papers, actually, so behind this last column that you don't see are many references per type of configuration, but none of all these papers basically utilize all the type of metadata that we could have defined on learning curve, basically data about data sets, data about algorithms, data about learning curves on the same data set, data about learning curves on other data sets, and that is absolutely something where a lot of potential is still. So my final words about getting involved, please do check out not just our survey, but also the other survey that Felix already mentioned, The Shape of Learning Curves by Loog and Viering. And please do try out some of the interesting resources on learning curves, namely LCDB and LCbench. And with that, I would like to thank you for your attention.
Right, thank you. Any questions? Yeah, go ahead.
I have a quick question. So far, the one thing you have introduced, okay, look at the or point. So you say no one to try to deep metadata, so that usually done on weekly help them. I guess we should do it. Or what I'm trying to ask is there a way from the model to protect learning curve to kind of evaluate on why the learners want to, or is it justifying the something?
Sorry, can you maybe? I hope that.
Asking is there a way to use metadata to detect why a model is not converging anymore and using that to?
Oh, that's a good question. So I'm not aware of any work that does address this question. Utilizing metadata to, of course, eventually all learning curves stagnate, right? So the answer is not why does it stagnate, but why does it stagnate at a certain point where it has stagnated. And my guess would actually be that the best way towards an answer for this is using capacity curves that basically say, well, this is the capacity of a certain model, and you have maybe now more data than this model could potentially handle. In relation to your original question, what about the meta features? I'm not aware of any work in that regard, and I also would not see any leads.
One more question.
Yes, Supervised. So one question I have is, of course, there's all these different methods that probably have different computational complexity, right? And a lot of algorithms are fairly quick to train iterations, right? So if you have some process in each iteration, calculate something, determine how complete you stop, that thing is expensive than being produced, right? So has there been any thoughts into the literature in terms of like trying to create systems that are very lightweight, I guess, relative to models to possible training?
Yeah, so basically, if I understand that the question correctly, is what you're saying is all these methods do use a certain amount of computational cost, and how does that relate to the final performance gain that you get, right?
Well, it's like, if I don't do, let's say that like I use fixed stations, and that's basically zero compute cost, right? And then I could train 500 iterations. But then if I use this advanced early stuff, maybe it takes the you and I go and train 400 iterations, right? Or train 500 fixed stations, right? Like that time stuff.
Yeah, so of course there's always an additional cost of using this type of there's also always an additional cost of using these type of methods. In general, in my experience, this additional cost is relatively low and does not compare to the cost of actually running the base algorithms. So that cost would be relatively small.
I think it would be interesting. Right?
Yeah, but I do think that most works do actually measure this as part of the wall clock time. So this is quite often measured. Thank you.